I am R. Prabha, Assistant Professor in the Department of EC, SNS College of Technology. In this lecture series, we are going to see the first topic as Introduction to Electromagnetic Fields. Electromagnetics embraces electricity, magnetism, electric fields, magnetic fields, and also electromagnetic waves. In electromagnetics, the emphasis is on the space between the conductors and the electric and magnetic fields within this space. So, the field approach of electromagnetics is essential for an understanding of waveguides, antennas, and waves in space and particle field interactions. Electromagnetics also provides a basic insight to the operation of basic circuit elements as capacitors, resistors, and inductors. Electromagnetics is fundamental to the advancement of electric and also the computer technology. So here we can see some of the examples of electromagnetic applications. So here we have the antennas, towers, and we have CCTV cameras and mobile phones, telephones, computer systems. So all the communication technology is based on the electromagnetic fields, and they are some of the applications of electromagnetics. And not only this communication technology, and also the electromagnetics are useful in computer technology and antenna technology, military and defense applications like sonar, radar also. This electromagnetic fields are very important. And another most important application is biomedical applications. So in biomedical applications, this electromagnetic fields are very much important, and some of the research areas of electromagnetics are antennas, microwaves, computational electromagnetics, electromagnetic scattering, electromagnetic propagation, radars, optics, etc. And if we see the introduction to electromagnetic fields, electromagnetic can be defined as it is the study of the effects of charges at rest and also charges in motion. So some special cases of electromagnetics: electrostatic charges at rest, and magnetostatic is charges in steady motion. And electromagnetic waves are the waves excited by the changes in time varying motion. And electric and magnetic fields are three-dimensional, and vectors vary in space as well as in time, governed by partial differential equations. And because of these reasons, electromagnetic field analysis is somewhat difficult, and the solution of electromagnetic problem requires a high level of abstract thinking, and we use mathematical for electromagnetics as a powerful tool. And consider a transmitter and a receiver. So here the transmitter and receiver are connected by a field. So when an event in one place has an effect on something at a different location, we talk about the events are being connected by a field. So a field is a spatial distribution of a quantity. In general, it can be either scalar field or vector field in nature. So the electric and magnetic fields are the vector fields with three spatial components. They vary as a function of position in 3D space as well as time, and they are also governed by the differential equations which was derived from Maxwell's equations. We know that Maxwell's equations are the basis for the existence of electromagnetic waves, and there are four useful equations derived by Maxwell's, and two equations are in scalar form and two equations are in vector form, and two curl equations and also two dot equations, that is divergence equations. And here if we talk about a scalar, we see a scalar is a quantity having only an amplitude. It may be a possibility phase. Examples are voltage, current, charge, energy, temperature. And if we talk about vector, it is a quantity having direction in addition to amplitude and possibly phase. Examples we can say velocity, acceleration and force. These quantities we know they have magnitude and that is the quantity, and also they have the directions. And there are fundamental vector field quantities in electromagnetics are electric field intensity E, and it is measured in volts per meter, or in the electric flux density, and it is also known as electric displacement, and its unit is coulombs per meter square. And next parameter in terms of magnetic field, the important parameters are magnetic field intensity, its unit is amperes per meter, and magnetic flux density, and it is measured in Teslas or Webers per square meter. And so we can conclude the important fundamental electromagnetic quantities are electric field intensity, electric flux density, magnetic flux density, and magnetic field intensity. And its units are given. For E it is volts per meter, D coulombs per meter square, B flux density it is Tesla, and H is magnetic field intensity in ampere per meter. So we can define a field is a spatial distribution of a quantity. It can be either scalar or vector in nature. And another important parameter is the velocity of the electromagnetic wave is C0 is equal to 3 into 10 power 8 meters per second. So this is the speed of light in free space, that is perfect vacuum. And another two important parameters in electromagnetics are, one is the permittivity of free space epsilon naught, and it is given by 8.854 into 10 power minus 12 farads per meter. So this permittivity is a physical quantity which describes how an electric field affects, and it is affected by a dielectric medium. And next is the permeability of free space. Permeability is the degree of magnetization of a material that responds linearly to an applied magnetic field. And permeability is a material property that describes with which a magnetic flux is established a component. It is given by mu naught is equal to 4 pi into 10 power minus 7 henries per meter. So assessment, the applications of electromagnetic fields, fundamental quantities of electromagnetic fields we know, and permittivity epsilon naught. Thank you.